Hi guys, welcome to Laplace Academy, and today we are going to continue our journey of learning how to simulate hydraulic systems in Simulink. And today I want to talk about another major component of hydraulic systems, which is a valve. And since valves need a full discussion and it's going to take a lot of time, I'm going to make several videos about different kinds of valves. And today we are going to keep it simple, just a shut-off valve, or it is also called a block valve or isolation valve or on-off valve. And by all these words, I mean that in these kinds of valve, we are only interested in a fully closed or fully open state of the valve. And the stroke is either fully open or fully closed. So I open Simulink, and in the library browser, I look for Simscape, and it is going to be an isothermal liquid model. Here, under valves and orifices, you can see there are different types of valves. You can see solenoid valves, shuttle valves, and all different types. Also, there are ball valves, gate valves, and so many other options. And as you probably know, gate valves are so convenient for shut-off use. But in this tutorial, we are going to stick to one of the most basic components of Simscape, which is a two-way directional valve. And there are two ports, which are the inlet and outlet of the valve, where the fluid enters and exits the component, and also it asks for a signal. And this signal determines whether the valve is open or closed or somewhere in the middle. So in order to have a complete system, I'm going to add two reservoirs, which must be isothermal. And now this is a complete system. So the fluid comes from this reservoir into this one, and it passes through a valve. It has to be a high pressure two-bar absolute reservoir. And the second one, I want it to be a low pressure 1-bar absolute reservoir. Okay, let me flip the block name so they're all on the left side, and I set it as a specified pressure of 2 bars. And also this one, I set it to 1 bar. So up until now, we have a complete system. The fluid wants to go from the high pressure source into the low pressure source. And by this valve, we can have a control on the water flow rate. So I also need a flow rate sensor. Here under the foundation library, I find isothermal, and under sensors, I find the flow rate sensor. I keep it as a mass flow rate for some reasons which I'm going to talk about later. So I make all the liquid pass through my sensor, and I add a PS Simulink converter and a display lock. And as always, we need a liquid properties and solver configuration block. I can create a group out of these two components and call it the settings of the system. And maybe I disable the content preview, and that's it. And here comes the most important part of this tutorial, which is how to deal with this component, this two-way directional valve. And I double click on it, and here are the settings. By default, it is a linear area versus spool travel. So as long as the signal is changing linearly, the area, which is the free surface of the liquid, is going to change linearly too. And there are all the different options here, we are going to leave most of them unchanged. For example, the smoothing factor, we don't need it right now, or the critical Reynolds number and the discharge coefficient. I'm going to talk about them later. And by default, the cross-sectional areas is set to infinity. And I'm going to leave this one unchanged too. But the first option I'm going to talk about is the spool position at maximum orifice area. So it means that if the signal coming into this component is equal to 5e-3 meters, which is 5 millimeters, if the signal is equal to 5 millimeters, then the valve is fully open. So I'm going to repeat myself. This value is the signal which is setting the valve 100% open. And the next value is corresponding to the value of signal for which the valve is 100% closed, or it is 0% open. So it is determining the fully closed valve. And just to show you how all these settings work, I'm going to create a PS constant block, and I will set it to 5e-3 meters. As I said, at this value, the valve is 100% open. And now let me run the model. So here is the flow rate for a 100% open valve. And as I said, if I increase the signal further, it is not going to have any effect on the simulation, since the valve is already fully opened. And if the signal increases further and further, it cannot be open more than 100%. So for example, let me double the signal. I run it again, and the flow rate has not changed at all. But if I reduce the signal, for example, by half, the flow rate has changed too. So if you right click on this block, and in the Fluids tab, you see the plot valve characteristics. And here the spool position is the signal that you may get from the PS constant block, which is this block. And it says that when you reach 5e-3, it is 100% open, and this is the orifice area. And if the signal is equal to 0, then it is 100% closed, or it is 0% open. And just to check that, I set it equal to 0. I send a signal equal to 0 meters, and if I run it, you can see that the valve is fully closed. But the flow rate is not exactly equal to 0, and the reason behind that is something called the leakage area. This is the minimum area of the system. So this component by default must have some minimum value for area, and you cannot set the leakage area equal to 0. So if I set it equal to 0, which means a fully sealed tight valve, MATLAB is going to show an error, and it says the leakage area must be greater than 0. So we usually set it equal to some really small number, like 1e-10, which is the default value. But you can also reduce it further, like 1e-15, and then the flow rate is going to be reduced massively. But it is going to have some computational cost to have such a small number. So I'm going to change it back to 1e-10 cubic meters. So if I reduce this signal further, and smaller than 0, meaning negative values, again, it is going to have no effect on the simulation, since at 0 signal, the valve is fully closed, and reducing the signal cannot make the valve more closed than it already were. So I set it to -1e-3. This is a negative value, and it is not going to change the flow rate, since the valve was already closed. Okay, so the component works like this. The first number is the signal corresponding to 100% open, and the difference between the first and second number is corresponding to the signal value, which is a 0% open valve. So as long as these two numbers are equal, then a zero signal means a fully closed valve. But if I set it equal to 1e negative 3, since it is the spool travel between closed and open orifice, then we expect the valve to be fully closed at 4e negative 3 value. So this is the easy calculation. 5e negative 3 minus 1e negative 3 is this, which is 4e negative 3. And just to look at the graph, I plotted again, and you see here at 4e negative 3 value, the valve is fully closed. And if I set it to 4e negative 3, you can see that I came up with the same value. If I reduce it further, 3e negative 3, the flow rate is not going to change because it is already fully closed. And now I want to talk a little about the flow rate calculations. So let me change it back to 5e negative 3. And as I said, at this value, the valve is 100% open. And here is the mass flow rate of the system. So we have a 1 bar pressure differential, and this valve is going to impose some pressure drop in the system, and there's going to be a flow rate corresponding to this pressure drop. But how is this value calculated? For that, I go to the MATLAB documentation of this component. And here it says that the calculations are for more details about how the block calculates flow rate through a variable orifice C orifice. So when the valve is 100% open, it just works as an orifice. So I go to the orifice documentation, and here for a constant orifice I have the formula. It says m dot is equal to these settings. So CD is the discharge coefficient, which is equal to 0.64. So I'm going to type this equation. It says m dot is equal to 0.64 times. Okay, the next item is the area of the orifice, which is this value, the maximum orifice area. It is the free surface of area when the valve is 100% open, and it is equal to 1e negative 4. So 1e negative 4. Next, it has to be multiplied by the square root of 2 times the density. So here is the square root of 2 times the density, which is approximately 999 kilogram per cubic meters. Then it has to be multiplied by the square root of the pressure differential. So again, multiplied by the square root of the pressure differential is equal to 1 bar, so it is 1e5. Then it has to be divided by this denominator. And I talked about the area of the orifice, and the area of the port is this value, which is by default set to infinity. So since the area of the port is infinity, then this fraction is going to be equal to 0, and 1 minus 0 is 1, and 1 times pressure loss is equal to the pressure loss. So it is equal to the square root of the pressure loss. But what is the value of the pressure loss? And if I click on it, I can find its formula, which is right here. And again, since the area of the port is set to infinity, then this fraction is going to be equal to 0, and then only remains a square root of 1. And the next term is again equal to 0. So the PR loss, the pressure loss term, is going to be equal to a square root of 1 minus 0 over a square root of 1 minus 0. So it is equal to 1. And you can see that this calculation gave me this mass flow rate, 0.90, which is almost equal to the value that the simulation gave me. So right now, you know how to modify this value. You know that the discharge coefficient or the maximum orifice area can change the flow rate or the hydraulic resistance of this component. So for example, if I double the area, then the flow rate is going to be doubled too. And then if I divide the discharge coefficient by 2, the flow rate is going to be divided by 2 too. And you may want to play with the cross-sectional area at ports A and B, just to see how this is going to affect the hydraulic resistance of this component. And that's it for today. I hope you enjoyed this tutorial and learned something. Please let me know in the comments what you think about this tutorial and what other tutorials you need. And please don't forget to hit like and subscribe button, and bye bye.